All right. Okay. All right, guys. So this is a continuation from what we did last time. So we were introducing the concepts of heat, right? And we said that the key takeaway message of heat is, here we go, energy transfer. All right. So that is the key. There is a transaction going on, okay? And energy gets sort of like moved from one place to another place. All right. So that is part of the thermodynamics law that we are about to learn. But the key point is, of course, for energy to be able to transfer, you probably have to deal with temperature somehow. That's why there is some dynamics that based on the thermal, okay, source. All right. There's some related to some things that are related to temperature that drive this heat flow. All right. But the business is not done yet. We have another half of the players that we have to understand. And this is what we're going to start today's lecture with, which is work in thermodynamics. All right. So this is a concept that we learned before, but we're going to have to reiterate this one more round for thermodynamic system. Okay. Every time we talk about work, you probably imagine like, okay, there's a force, there's a distance, and then you have to do some calculations. We're going to have to do that again here. All right. One more round. But once we have that, then we are going to be able to combine them with, we already understood the internal energy, which is just the total energy of the system. And eventually today, you're going to get to see what is the first law of thermodynamics. Okay. All right. And once we get to that, then you can do a lot of stuff. All right. A lot of things can be done with this law. So this is good. Okay. All right, guys. So in general, once again, I don't know why, but just FYI, thermodynamics used to be the subject that I hate the most in physics. Initially, it was just like so many equations, so many quantities, constants, formulas, relationships, and everything is just like, it's feel like biology. Okay, it's just like so many things, just too many things, have to memorize a lot. But in the end, it's still physics anyway. So this is what I'm trying to say. You remember the concept of work before, hopefully. All right. So when we talk about work, probably in your head, F dot S, maybe, yeah? Or maybe you just said it's a force multiplied by the displacement in the direction of force. Yeah, that was the way that you calculated work before in Newtonian physics. We don't want to do it here anymore. We talked about this last time, that thermodynamic system is just like you have system that composes of huge amount of molecules, particles, objects, and everything. You cannot do it one by one anymore. So how can we get away from that force? Because who will want to talk about force that's acting on a molecule, right? That would be crazy, right? And who will want to know how far the molecule has been traveling in the past second? Nobody can measure that. That's impossible, right? So how can we move away from this expression? And it turns out in thermodynamics, we transfer this, it's not transfer, it's sort of like we manipulate this and try to express in something that we have already familiar with from last time. We turn this into P and change of the volume. There you go. All right. So this allow me to just cut the detail. Usually just this slide alone, I spend like 15, 20 minutes talking about the history of force and, you know, displacement and stuff, and then do the conversion and stuff. Forget about it. The key is this. I'm just going to do a simple dimensional analysis for you. Force is Newton. Displacement is in meter. Okay. Pressure, if you remember, is the force per area. So that means pressure is going to be Newton per square meter. That is a pressure. But the volume is cubic stuff. So it's going to be meter cubed. So if you just look at the dimension, it looks nice. At least these products of force and displacement share the same units as the P multiplied by the volume. Okay. And not only that, of course, that means pressure and volume will give the amount in joules. So it means it's an energy. It's an energy. Okay. But then there is a delta in it. There's a change. There's a change. So that is exactly what we want. Work is also an energy transfer. You got it? Work is also energy transfer. So when there's a transfer of energy, you expect something to move. But in gas, the signature move of gas is volume change. It's either expand or contract. That's how gas can behave in terms of like, hey, I'm changing my shape. So it means there's some displacement going on, but we don't want to deal with it individually. We want to deal with them in the collective ways. The whole system expands, the whole system contracts. Sounds good? So that's why this is it, guys. Pressure times the volume change. But of course, you can turn this into an integral if you want. But I already talked to you like, hey, we try to minimize the calculus stuff in here. But I mean, this is not too hard to understand. It's just the pressure times the volume change, but you do it a tiny bit at a time, and then you sum them up. So that effectively, this is still the same meaning as the pressure times the volume change. All right, but this is just in case that you have to deal with like change of the volume that looks weird, and then you cannot calculate it easily with algebra. You might have to use calculus a little bit. But anyway, let's stick with the notation, but we're not trying to do calculus here, so don't worry about it. But this is the conclusion. You can calculate the work done by doing the pressure multiplied by the volume change. Done. Okay? But Bachan, wait a second. Why you have two boxes here? There's one box on the top, there's a negative sign in the front, there's another box in the bottom without the negative sign. So here comes the trouble, a little bit of trouble. Then there are now two sides of the universe. If you look at this diagram over here, or this figure over here, there is a gas inside this container, which is there's a movable piston. So it means gas can expand or it can get contracted depending on the movement of the piston, yeah? All right, but then the point is, think about it. If you notice that this gas gets contracted, there are two ways that you can explain this. You might say that, hey, there must be somebody compressing or pressing down this piston. So that's why gas get compressed, right? That you say there is an external force acting on the gas. Sounds like a good plan. But on the other hand, from the perspective of the gas, you feel like somebody else pressing down on you. So if you are this system itself, you will know you get compressed down. So it's just the opposite side of the same situation. You guys with me? So if I am the external people over here that I'm trying to press it down, I'm doing a positive work because I'm pushing it. But if you were to be like, I am gaseous system, I feel like I'm being compressed. With me? So that's why there is that's going to go one direction, the other will go opposites. One will be positive while the other one will be negative all the time. Think backward. If gas want to expand back, all right? Gas expands. So let's say we are gaseous system. So we are like gas molecules. Well, gas expands this room out. We are doing the work, right? We have to help each other to sort of like push the ceiling, push the wall and everything, right? We are doing the work. But if I am the guy outside this room, I would say, hey, gas pushing me back. I get a negative work done. Does that make sense? So if one work done is positive, the opposite side will feel the negative work. So that's why we have to pick one. And this is what we do right here. In the bottom, initially, I will do a subscript over here, say, hey, work done by the system is just a positive work done, of course, because that is the gas system doing the work themselves. But if you think of it in an opposite sense, what about the work done by the external agents? You just have to put a negative sign in the front. Sounds good? All right, so this is just to clearing things out up a little bit about the sign. Why am I doing this? Because the textbook used the red box. The textbook, our reference text, used the upper box. But some textbook, because I said before, you can read any physics textbook in the library or wherever that you download. Some textbook use the bottom one. All right. So what I'm going to try to show you here is in the end of today's lecture, there will be no ambiguity. Everything will look exactly the same. Don't worry about it. All right. But for now, at least you understand, we stick with this. And this is work done by the system. And that's what we're going to call W for our lecture right here. And you will hopefully will agree with me that is an easier way to think about what is going on with the gas. Otherwise, then you have to flip the sign all the time. It's going to go crazy a little bit. So stick with the system. Stick with the system. Okay. All right, guys. So that is what it is. Work is energy transfer. For the thermodynamic system, like gas, like what we are doing right now, you can calculate it through pressure times the volume change. Sounds good? All right. So that is done. That is done. All right. We are getting better. But wait a second. There is even a better, it's not a better tools, and helping tools that allow you to do the calculation just a little bit easier if you incorporate something we call a PV diagram. All right, I am not so sure that you seen this in chemistry before. I remember vaguely I did it in chemistry as well, but somehow when I talk to many freshman students, they say they haven't seen this before. But anyway, so if you haven't seen this, this is it. We call the PV diagram because it's a PV diagram, right? One is a pressure, one is a volume, that's it. All right, but the reason that is very good because you remember we had equation of state, PV equal to nRT. So P and the V is 2 out of the, well, you count 2 out of 3. Let's say that's a pressure, volume, and temperature. So you pick the first 2, the pressure and the volume, and you do a plot showing what is the behavior of our gas. Sounds good? All right, so by knowing these coordinates, you know the pressure and you know the volume of the gas. So if you know the amount of the gas, you will be able to determine the temperature of the gas right away. Sounds cool? All right, that's one thing. Second thing is by tracing a curve on this PV diagram, you can bring your gaseous system from one point to another point. So this is called process. You try to treat your system in some way. For example, try with me here. From here, initial point, you have initial pressure, you have initial volume. What you're doing right here is, Bajan, I want to here compress the gas. Got it? Volume decreases, you're compressing the gas, but during this compression, the pressure is constant. That's okay, right? That's where this line is telling you. Once you're done with the compression process, you fix the volume and then you increase the pressure to the final value. This is how this process is being done to the gas using a PV diagram to explain the process. Sounds good? Try again. This one, Bajan, I want to do a different way, even though I want to start at the same point, I want to end at the same point, but I want to do it this way. I want to increase the pressure first, keeping the volume fixed. And once I reach the final pressure, then I contract the volume later. That is fine. No problem. That is another process that you can do. Okay. Or, but then, yeah, it's not fun. Why don't you just shoot right away? I can just start from the initial point and I'm just going to aim for the final this way. That is also fine. See, so anything is possible in PV diagram. All right. These lines will tell you what is going on with your system. But the benefit of having everything laid out in the PV diagram is, can you see the highlighted area under the curve? Can you guess what it is? Very good, very good. Whatever you're thinking is correct. Yes, yes, yes. Very good, very good. P is Y. V is X coordinates, right? So if you care about the area under the curve, everyone still sort of remember from calculus, area under the curve is just integral y dx. Sort of remember vaguely? Yeah, yeah. Anytime that you have a function y as a function of y of x, f of x, you do the integration of y dx, you get an area under the curve. But from what we are seeing over here is the pressure is a y-axis, the volume is the x-axis. So if I do that here for the PV diagram, isn't that nice? And that's it, guys. It's the conclusion. Area under the curve is telling you the amount of work done during this process. Isn't that nice? That's cool. That's cool. So this is why PV diagram is very useful. we will be able to tell the state of the gas by looking at the coordinates, P and V, and then all the stuff. Plus, we know the line. The line will give you how you want to treat your gas. Okay, which process we're talking about. You want to expand, you want to contract, you want to do this and that. And the area under the curve give you the work done during this process. Perfect. Okay, sounds nice. All right, so this is a tool that we have that allow us to calculate the work done quite easily. All right, so now we got the concept or definition of work in thermodynamic system down. We see a little bit of the PV diagram. This is good. What's next? All right, here we go. Let me make sure that you get it. You're going from point A to point B, like we saw a lot previously. You can do it in so many ways. You can see that path number 1, path 2, path 3 give you the different area under the curve, yes? So that's why by knowing the initial points and final points, will not be able to tell you how much work is being done. The only thing that will allow you to calculate the work done is you have to know exactly how the gas is being processed. Sounds good? So that means you have to know exactly which line that bring the gas from point A to point B. This is important. So one conclusion that we have here is work is depending on path. This concept is already known back in the day of Newtonian physics. For you to be able to calculate the work done, you have to know exactly what is the displacement, right? So that's why you have to know exactly how things go. Okay, so that is one comment over here. But the point that I want to do that here is let's practice how things can sort of like get questions and ask you to do some calculation here. You have an ideal gas undergoes a constant pressure expansion. See that? So when you see this one in your head, that this is good, this is good. Constant pressure. So you imagine that it must be something of a horizontal line because pressure must be fixed. Sounds good? And another one is saying that it's an expansion. So it means it's going to start at some volume and it's going to expand to the right. So I have an arrow pointing right there. Okay, expand, expand. And not only that, we know that initial volume is given, the final volume is given. So I will be able to pinpoint the initial volume to be 2, the final volume to be 4. And everything is in cubic meter unit. Very good. Okay, okay. So find the work done by the gas. When they say by the gas, this is exactly W of the system. Okay, okay, cool. And we might just call it W because we're okay with the concept here. And we know it's just PdV and it's just area under the curve. All right, so this is kind of like a summary that I want to get you to this point right here. So this is a takeaway message for this early portion of the lecture. You can calculate work done by either do the integral PdV, or if you are given a PV diagram, get the area under the curve. Okay, okay. All right, and over here, but now John, look at it. This is gonna be pretty easy because it is going to be just a rectangular area. Very nice. That's easy to calculate. All right, and then we do it right away, but John, okay, go for it. This must be the work done. It's just gonna be integral. Okay, let me do an integral sort of like way of writing this one, but you will see it's going to turn out to be very easy because pressure is constant. I can pull out P, okay, and leave the integral behind, okay? And when you do the integral of the dV, all you are getting is just V final minus V initial. Everyone good? Okay, and that is just P delta V that we were talking about. And that is simply the height times the width. Isn't it nice? Sounds good. All right, so hopefully this showcases everything that we have been talking so far. Okay, but this one is good because area under the curve is just a rectangle, so it's easy to calculate, but it's confirmed. No matter what you want to do it in a calculus way, you do the integral, you're done with it, you get, hey, with the constant pressure, the area is simply pressure times the volume change, but this is exactly width times height. Same thing, everything is just fall into place. But here comes one pitfall, making sure that you do the delta properly. Why? Look at this. Keep going. If I substitute P as 1 ATM for now, all right, we're going to worry about the unit conversion later. Just leave it as 1 ATM at this point. And the volume change is going to be final minus initial all the time. This is crucial. The reason that you have to pay attention to the order of subtraction, because right now it's going to look like, okay, I can convert this into Pascal. Don't have to memorize this. I'll give you the conversion factor and everything. And then the final volume is 4. Initial volume is 2. The answer is positive. Work done. Everyone with me? The answer is positive. Means gas does the work. Gas expands. That's why it's a positive result. Okay, that's why order of subtraction is important, because now we understand that if you flip this sign, everything will go reverse. Gas get compressed down, which is not the case. Over here, we have an expansion. So we expecting the result to be positive because gas expands. Gas does work. Okay, good, good. All right. So it's sort of like everything has to come into the same place, no matter which approach you try to take. Area under the curve, formula, calculation, behavior, everything has to coordinate each other perfectly. All right, sounds good. All right, not bad. It's a warming up problems right here. It's gonna get a lot more fun later. Guys, actually, I love this thing, right? It used to be the first topics that we study in 102, but then as I sort of like switch it up a little bit, so we started with the oscillations and simple harmonic and waves and other stuff. But in the syllabus, originally, we should start with thermodynamics. Right? But anyway, I think it's better to end this course with this one because it's kind of like easier on the mathematics and everything. All right, guys, try this one more round. Everyone try this yourself first. I'll give you like a couple minutes head start. 3 mole ideal gas, okay, undergoes constant pressure process again. Oh, all right, we got it. Constant pressure expansion. So in your head, Bajan, it looks almost the same. It must be a horizontal line. You're gonna start somewhere because it's expansion. You're gonna end up somewhere bigger in volume. So you put arrowhead pointing right on it. That's okay. That's good. But it turns out the information that you're having is now initial and final temperature. Whoa, whoa, whoa. Here we go, guys. Find the work done for me. Going from the initial point to the final point. Okay, Bob. All right. If you cannot sort of think of anything else, start with the expression of work done first. Work done is just integral PdV. But because pressure is constant, P is out. And the integral of the dV turned out to be just a delta V, the change of the volume. Okay. And because this one, you know exactly what should be in the final volume, you know exactly it's going to end up at some point at the initial volume. You might just call it V final and V initial. But unlike the previous exercise, we do not know the pressure and volume this time. We know temperature. And that's where your equation of states come into play. PV equal to nRT. Got it? Yeah? So you can always turn this PV product into an nRT instead. So what I can do is, Ajahn, it's going to be nRT final minus nRT initial. Yes? All right. And this is it. Your job is done. N is 3. That is the number of mole. That is a small n that we were talking about. the amount of gas in mole units. So that is small n is 3. Actually, R is R, so let's leave R there. I can actually just wrap n R together and just take the temperature of 400 Kelvin and then subtract out the 300 K. Sounds good? All right. And once again, the order of subtraction is important again, because you have to take the final temperature first and subtract out the initial temperature. In the end, you stick with, you got a positive result, which as expected, 300 R joules. Sounds good? And I can just emphasize that it is positive. Why? Of course, Ajahn, it has to be positive because that is an area under the curve. Right here. It's the same type of area under the curve. It's still a rectangular area, so that should be okay. But the information that is given to you is now temperature instead of pressure and volume. No, not bad. This is not bad. All right. Okay, getting better, getting better. All right. Just to give you some motivation, by the end of this unit, you will understand why can't you use your body temperature to charge your phone. You must have thought of this, right? Your body temperature is 37 degrees Celsius. Your room temperature is 25. You're losing energy all the time. Right now, your body is hotter than environment. Why can't we extract energy from our body, put a USB port in your shoulder, and then just charge your phone? Yeah, collect all those releasing energy, and then yeah, like when you work out, your body is getting hot and stuff. Why can't you just squeeze that extra energy that you're gonna have to release out into the environment and then charge your phone? Something like that. All right, so the answer is in thermodynamics. Or even better, by the end of this unit, you will be able to see what is going to be the best engine in the universe. Even Tony Stark cannot build a better one. Yeah, as long as he's using physics and not like whatever vibranium stuff there. Yeah, that will be this in thermodynamics here. All right, here we go. Try again. All right, so this is used to be the O exam questions. So hopefully it's going to be somewhere around here, at least to ask you to figure out what is the amount of the work done. All right, determine the work done on a fluid. See, in reality, you don't have to stick with the gaseous system. We don't care because it could be fluid, it could be solid, it could be anything. Okay, but as long as it's not a gas, you cannot incorporate PV to nRT. That's all. But for a regular interpretation of the PV diagram, the interpretation is exactly the same. Area under the curve is the work done. Here we go. You have gas expand from initial point to final point according to the PV diagram below. Find the amount of work done. Actually, we don't even have to calculate it, but then just do this. Find this area, okay? All right, and let's assume if this area is A, you get a number. What should be the answer for part A? The work done going from I to F must be, you should be able to answer right away, it must be positive A. You guys with me? Why? Because from I to F is an expansion. Gas expands. Sounds good? And in part B, they say, hey, if they want to reverse, you want to go from F to I instead. What would be the answer for part B? The work done going from F to I following the same path. All you have to answer is negative of the same amount of area under the curve. Sounds good? All right, so don't think too complicatedly. This is it. All right, it's simple as finding out the area under the curve. If it's an expansion, it must be a positive work done by the gas. If it's a contraction, it's the same amount, but it's a negative work done because gas get compressed. Simple. Okay, all right, and you don't care about the shape of the area under the curve. As long as you can figure that out, you can assign the sign and move on. Done. Okay, not bad, right? This is not bad. So everyone now is equipped with how the work can be calculated, especially if you are given a PV diagram. So everything works out really well. Now, what do we have on hands right now? All right, are you guys ready? Here we go. Things might be complicated, even though I'm not going to use this in the exam anymore if I keep my promise not to do calculus. But now you can acrobatically solve any problems, any curve, any process, as long as you know a form of the relationship between the pressure and the volume, like this. This one, just quickly, don't worry too much, guys, but this is it. If I want to find the work done, all I need to do is finding out the area under the curve, integral PdV, yeah? This is just for fun. And because you know how to write P as a function of V, here we go. And then you start from the initial volume to the final volume. You do the integral a little bit, you get V cubed over 3, and then you substitute the initial and final point, and that's it. Your job is done. V final, okay, I can even put the numbers there, 2 cubed minus 1 cubed, and that's it. It's 7/3 alpha joules. Positive, yeah, of course, it has to be. Okay, so just FYI that even though we're not going to focus on the calculus stuff, but this is where this formula can sort of like give you an ability to do any work done calculation. It's an area under the curve. That's it. All right, that's the whole point. Okay, very cool. All right. Now you are ready. Almost. You're almost ready. All right. The fun is about to begin right here. Now, let's do this. This is, I think, the most important figure of the day. If you understand this figure, you automatically understand the first law of thermodynamics. Seriously. Yeah. All right, guys. Look at the left one. The right one is going to be discussed later. But for now, stick with the left side of this figure. All right. Imagine along with me. Now you have a gas in a container, okay? Now this container is actually insulated, so that's okay. There's no heat flow in or out, except on the floor, okay? The bottom of the container are in contact with, I'm gonna explain a little bit, something we name reservoir, okay? Leave it there. Let's connect to the outside world. The gas actually start with the temperature of T sub I. The energy reservoir is also the same temperature. This has to be. Think of it this way. Let's say we are gas molecules. Okay, sounds good. All right. So we are the gas particle in this. The bottom of our classroom is connected to Salaya campus. Sounds good. Okay. If right now we don't have the make sense? Okay, all right. But if you together, make it warm, there's no way that you're going to be able to warm up Salaya campus. Oh, no way. Why? Because Salaya campus contain a lot of thermal energy. That's why we name it a reservoir. Sounds good? But because we already have the connections, energy is temperature. So if the Salaya campus is at 30 degrees Celsius, you're not going to be able to change it. It's going to stick at 30 degrees. That's why our room will be at exactly the same temperature. Sounds good? All right, got it? So that's why I have this gas in thermal contact with the energy reservoir at fixed temperature. It's a guarantee. This gas must have the same temperature as this one. I mean, you can think of it, it's gas going to be part of the reservoir anyway, right? We are just as a classroom. We're not going to be able to do anything significant to Salaya's temperature anyway. So whatever Salaya temperature is, that's going to be the temperature of us too. That's it. Okay, cool. That's what it is. Now, turns out we expand. Somehow the ceiling of our classroom get expanded, pushed up twice as big. So the gas, us, have more rooms. So the volume of this classroom doubled. What happened? That's the question. All right, think about it. This is weird, a little weird, right? So we are gaseous molecule. So we're bouncing around in the room, okay? But then we said about, hey, Ajahn, the room is a little kind of like cramped. Can we push the ceiling up a little bit more? Yeah, okay, why not? So you guys help pushing up the ceiling. So the ceiling is sort of like moving up, 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 up. So we double the volume, all right? What happens to us? First thing first, work done is positive, yes? Because gas expands. We expanding the room. So we doing the work. All right, all right. Work done is positive. Everyone good? But we said work is energy transfer. Where do you get the energy from? Of course, you probably had breakfast. Yeah, breakfast. Yeah. So you have to spend that energy pushing the ceiling up, right? So in general, you have to spend your energy out. So by pushing the ceiling up, in a normal circumstances, your level of energy should be down. You spend your own energy to do the work. Does that make sense? With me? In general, if you want to do something, you have to spend your body's energy and do it. You spend your energy doing something. That's why work is energy transfer in general, right? You transfer energy from your body to something else. But the problem with this one is your temperature stays the same throughout this process. Remember, we are part of the reservoir. But we said temperature is energy. So that means this process, during pushing up the ceiling, the condition is your energy must stay the same. How can you do it? Think again. You pushing up the ceiling, you perform some work, but the condition is by the process, your energy level must stay the same. How could that be? You're doing work, just your energy level must stay exactly the same as you started. So that compensate for that. Does that make sense? What would that be? Very good. Whatever you're thinking is correct. I don't know what you're thinking. All right, you do the work. It's a positive work. The energy does not change. So let me name the energy, where we name this internal energy U. But because temperature is fixed, no energy is changed. I said no change, delta is 0. How could that be? Yeah, there must be heat flowing in. Everyone with me now? ไม่ค่อยตื่นเต้นเท่าไหร่ No? Jaw dropping moment a little bit? No? No? All right. So this is what the thermodynamic is about. Over here, all right, you do the work, but wait, Ajahn, the condition is you cannot change your own body temperature, the body temperature stay fixed. So your energy level stay the same. So how can you spend energy to do some work? There must be something give you that extra energy, and you use that for this work done. So that must be some heat flow into this. That is thermodynamics. It's so dynamics. There's a work going on here. There's a heat flow over the of energy of this system. Sounds good? That's it. So these are the main components in the first law of thermodynamics. Heat, which is energy transfer. Work, energy transfer. Those two will affect how the energy of the system is changing. First law of thermodynamics, guys. That's it. Okay, sounds cool? This is a conclusion right here. Bam. Heat, work, affect the change of the energy. But the reason I have 2 boxes is, once again, in case that you read the textbook, if you see any textbook using the negative sign, that is the W of the system. If any textbook use the plus sign, that is the work done by the external force. But as I promised, no matter what you do, if you write down like this, Q, and then you substitute the formula for the work done, they're going to look the same no matter what. Everyone with me now? All right, because we agree that the W of the system is just PDV, integral. With the negative sign, if you're going to collectively call the negative integral PDV, you can wrap it and call it the W external. Yeah, so it doesn't matter. If you write down the full expression in the mathematical ways, that these two expressions will merge into exactly the same relationship between the change of the energy, the heat, and the work done. Guys, first law of thermodynamics is in front of you right now. Wow. Okay. So let me ask you one more question before we take a break. If I warm up a gas, the temperature of the gas is supposed to rise, yes or no? If I give some energy to the gas, let's say if we are gaseous molecules, remember we are in classroom and then somebody burned something underneath us. So we as a gas has to rise in temperature, yes or no? That sounds reasonable, right? Yeah. But let me ask you another question. Why this process is going on? Somebody burning this classroom. Is it possible that we get colder? Is it possible that if we warm some gaseous system, maybe burning it, then that gaseous system get lower in temperature? Is that possible? And the answer lies in this first law of thermodynamics. If your thought was saying yes, Ajahn, that means you probably thinking that the gas has nowhere else to do with that energy. With me? Because when I warm up the gas receives that energy, it has to rise in temperature. That makes sense. That makes sense. But now, because we know better, if the gas is allowed to expand, there might be a possibility that the expansion is so fast that the work done by the gas is actually more than the energy that gets from the fire or whatever things that warm it up. So the gas could be cooler. Does that make sense? Just to give you a perspective, have you played with the spray can? When you spray something, the can gets so cold. Why? Because gas expands out so quickly. So they're doing some work done. So it loses some energy. So that's why the temperature drops so fast. But think about it. If you're doing the spraying and then you put the lighter underneath, which you shouldn't do, all right? But that is an idea. Of course, the gas is still cooler no matter what, because the expansion is so huge, right? The fire from the lighter probably not going to be fast enough to transfer energy to the gas and make it warmer. No. It's still colder anyway. Make sense now? That is the first law of thermodynamics right here. From this point on, you have to ask me back. Let me rephrase the question one more round. If I warm a gas up, gas has to increase in temperature, yes or no? You have toบอกอาจารย์ does the gas expand? With me? You have to ask me back first because your information is incomplete. You don't know the behavior of the gas. Until I said, oh yes, the volume of the gas is not changing. Then you said, okay, Ajahn, for sure, gas must be warmer. Got it? Sort of get an idea? So right now, what you are having is, it's the three-party. It's not just like heat and temperature anymore. There is the work come into the party. So you have to make sure that you know the information in both of them, not only one. You cannot. You have to be able to understand what is going on both sides of the energy transfer. And now you have two ways. It's either the heat or it's work. You have to know both before you will be able to determine what is going on with your energy of the system. Sounds good? It's kind of fun. All right? And don't worry, Bajan, How can we calculate this amount of work done, this amount of energy? We got a lifesaver right here, guys. This is what we called it the internal energy before, the total kinetic energy of the system. And this is the conclusion, guys. 3/2 nRT. Woo, very nice. So this confirmed that for the gaseous system, that's why we study ideal gas. If it's a monatomic ideal gas, the total energy, okay, of that system can be calculated simply by knowing its nR and temperature. See, perfect. This is what we want. We know that the temperature indicates the amount of energy in the system. And this is the exact formula to calculate that. Okay, all right. So we have major components. We are ready for the first law of thermodynamics. So after the break, we'll get to see how this thing gets applied to the real problem. Okay, and things will start to get a lot of fun from this point on. I hope. We will see. We will see. Already. All right, take a break first, guys, and we'll come back with the real first law of thermodynamics analysis. All right, so we're gonna try answering some of the questions that now starting to use that first law of thermodynamics. As you notice, every time that we try to deal with this, there are three components all the time. Either delta U, the heat, and the work, right? It's gonna go on and on and on like this until the end of the whole universe, pretty much. All right, here we go. You have a process according to the PV diagram on the right. Fill out the blank in the table. All right, let's start from an easy one. Look at this. You're gonna go from A to B. A to B. What do we know? Going from A to B. At least you should be able to tell Ajahn, the work done must be positive, right? With me? Because it's expanding. So I should be able to write positive sign here right away. However, because it's already given in the table that the delta U is also positive, here we go. From delta U equal to Q minus W. Don't forget our W is a W of the system all the time. All right, we use the negative sign here. So Q is just delta U plus W. However, we just realized that delta U is positive, W is positive, so it's guaranteed that the Q must be positive as well. Sounds good? All right, so by doing this, it just means that during this expansion, the pressure is constant, work done is positive, and there's a heat flow into the system. Right? Because we agree that positive heat means heat is flowing into the system. Okay, sounds good? All right, try again. Going from B to C. Now it's up. B to C. What do we know? Okay. What we know is there is no volume change. Whoa. No volume change means W is 0. Okay? So when the W is 0, you already given the Q. So you just, once again, using that, Q is positive, W is 0, delta U must be positive as well. All right, so get a sense of what is going on here. All right, so you must at least know 2 out of 3 before you'll be able to determine whatever the unknown is. All right, there are 3 parties in this relationship right now. Okay, not bad. This is not bad. All right, this is not bad, but it's quite too simple because there are already some clue given in the table. So let's redo this one more round for another process. Okay, try again. So everyone good? Let me do this one. Now you have something, we call it a cyclic process. The process that comes back to itself is come in cycle. It's a cycle, cycle, cycle. A, B, C, A, B, C, A, B, C, A. Keep going. Draw, once again, determine the sign of those 3 parameters, the delta U, the Q, and the W, during the change from A to B, B to C, and C to A. Okay? All right. So we want a table again. So let's sort of like a copy from what we just had. So we want to know what is going on. with the delta U, with the Q and the W, going from A to B first, shall we? All right, guys, this time there is no clue. Okay. All right, fill the table for me. Just a second. Okay, what should be signs, guys? What should be the sign? Okay, what do we know? Going from A to B. Oh. There you go. Going from A to B is an expansion. See, right? Is an expansion. You can even know the area under the curve. It's going to be somewhere here, even though we don't need to calculate this problem here, but that's what we have. Positive, for sure. What else do we know now? You have no given clue anymore. What do you think? Going from A to B. W is positive, but what else do we know? And here comes the tip of the day. All right, so I don't know where and when this thing will show up from time to time or not in the future, but I think this is something that we can incorporate right away. Come back here a little bit. This process right here, there is a particular shape that actually, if this one taking that shape, it's coming from this, guys. PV equal to nRT, right? P is Y, V is X. If this right-hand side is a constant, think about it. When the right-hand side is a constant, what does it mean? It means the temperature is fixed. It's a constant temperature, let's say. So the right side of this equation is just a number, yeah? So you will gain a form of the equation that looks like X, Y equal to C. Have you seen this equation somewhere before? If you treat the right side of this equation, the equation of state, to be just a constant, P and V, which is our X and Y coordinates, gonna be a product that is equal to a constant at all times. Do you know the shape of this curve? X, Y equal to constants? There must be something going on in the past. And that curve looks like this. If I want to draw it briefly, it's going to look like this. Have you seen this? Yeah. X, Y equal to constant. So it means when X is big, Y must be small. If X is small, Y must be big. It's sort of like the product stays the same. So that's why there is a curve on the first quadrant to look like that. Or if you want to go the opposite quadrant, the third quadrant is going to go opposite like this. All right. That is something happening here. With me? So anytime that you are at some particular temperature, there must be a line at that temperature that allow you to draw this curve all the time. So this curve, which is reflecting of this curve right here, this curve is a constant temperature curve. If your system has one particular temperature and is unchanged, you cannot get out of this line. You have to stay in this curve at all times. Does that make sense? Okay, got it. We call this isothermal line. Iso means the constants and thermal is just temperature. But we'll come back to this. But that's the idea. What does it mean? If the temperature is different, you must be on a different curve, right? Because one temperature will have one curve of its own. Different curve, different temperature, different curve, different temperature. And the bigger the constant, this means the bigger the temperature, the line is gonna go higher and higher, higher and higher. Okay, use this idea, come back here. What do you know? Well, Ajahn, that's nice. Point A must be on one of the isothermal curve. Point B must be on another isothermal curve. Point C must be on another isothermal curve. Does that make sense? So whatever point on a PV diagram, there must be an associated temperature, and that temperature must be on one of these lines for that particular temperature. Does that make sense? By knowing going from A to B, you definitely gonna jump from the lower lying line to a higher lying line for sure. Right? You get out of it to a higher lying one. So it's a guarantee going from A to B, your temperature is increasing. Does that make sense? All right. So with that, Majan, A to B is increase in temperature, and temperature rising, energy is also rising. That's why delta U must be positive. And once your delta U is known, W is known in value, then you said delta Q is just delta U plus W is a guarantee that Q must be positive as well. Done. That's how it goes. This is the qualitative question. So imagine that what is going to happen next is we're going to have to calculate it quantitatively. But this is just a warm-up question. Try again, guys. Let's go from B to C, shall we? All right. Oh, Adan, I kind of get it. Going from B to C, the area under the curve can be found. The gas is still expanding. Yeah. Gas is still expanding. So it's a guarantee that the W must be positive. Okay. But then with the same trick, but this time is jumping down. It's get off from the the higher lying line, the B point, and come down to the C point. So this one is a guarantee that you're going to get a negative change in the energy because temperature is lowered. But then, of course, you might argue because you don't know the scale of the and all the stuff. The Q might be a questionable. That's okay. All right. But if you know numbers and everything, then you can compare and contrast the two, which one is bigger, which one is smaller. Yeah. And then you know exactly what should be the final sign. But at least, yeah, it's just a sum of the two. Sounds good? Last one, going back from C to A. All right, going from C to A, of course, area under the curve is down here, but this time it's a compression. With me, guys? It's a compression because now you go from C back to A. Volume decreases, W is negative. This is a negative work done, so you know it must be negative here. And look at the isothermal line. You're jumping off from the C point, which is a higher lying isotherm, jump down to point A, which is lower. So you know your temperature is down. Delta U must be negative. And it's guaranteed if both of these terms are negative, Q must be negative as well. Heat leaves the system. Q is negative. Isn't that cool? I don't think there's anything cool about this one, but it's annoying. Right? You start to see why things going to get kind of annoying over time because there are so many things that you have to calculate. You have to calculate W. To do that, you might have to use equation of state, and then you have to calculate the delta U, and to do that, you have to use another formula, and then you come back to the Q to know this, and then you have to know the other two first, on and on and on. So the process is going to be tedious, but that's the way it goes. This is a lot of stuff that is happening. Okay, guys, give it a sort of like get a bigger picture what is happening here. All right, now we're going to get a little bit more and more into it and see how things go. A system undergo a cyclic process again, so it's a complete cycle. Find the change in the internal energy at the end of each cycle. Part A. What is the change of the energy after the whole cycle? A, B, C, D, A. Very good. Whatever you're thinking is correct. It's back to the original point. No change. Everyone good? Because energy is path independent. Depending on temperature, So if you come back to the same point, it's the same temperature. So there's no difference in temperature. All right. So anytime that you have a cyclic process and you want to find the total change of the whole cycle, of course, there's no change because you bring your system back to the original point. So whatever you do, you compensate it back and everything just get back to the original shape. So no change. Part B, find the total work done for each cycle. All right, this one is a little bit better because now we know how to do that. But once it's a cyclic process, something is nice happening here. You're going from A to B, the work done is going to be area under the curve. So let me highlight it in yellow. There you go. Yeah. And everyone knows going from A to B, it must be positive. WA to B must be positive. It's a positive yellow, yeah? Okay. Now going from B to C, you get nothing because it's a vertical line. No volume change, no volume change, no work done, nothing is happening. And now you want to go back from C to D. And this time the area under the curve is only the bottom part of this whole thing here, the green one. Yeah, but this time is negative though. Okay. And then you go up from D to A. Then everything is just zero again because going up vertically, there's no work done. But think in terms of the geometry, going from A to B, you get a yellow shaded area, positive. And then going back from C to D, you have a green area is a negative one. So it's exactly the same as you want to erase the yellow out by the green. Does that make sense? So the green part cancels out the bottom half of the bottom part of the yellow. Yeah. So that's it. The net work done for the cyclic process is just an area enclosed inside the cycle. So the answer will be the W going A, B, C, D, A is just area enclosed by the cycle. That's it. Make sense? All right. It's coming from the positive part from A to B and erase down the negative parts coming from C back to D. And from here, you can simply calculate it by, it's the width times the height. So the width is going to be P1, the height is P1 minus P2, and the width is just P2 minus P1. Done. It's just a rectangular area. Nice. Not bad, not bad. And everyone good? And part C is going to be simple now because part C is asking for heat. From the first law of thermodynamics, I move W to the same side as a delta U. So heat is just a sum of the delta U and the work done by the system. Because the work done is known, the delta U is gone. So the answer is whatever part B is, that is the Q also. Yeah, yeah. So the answer will be exactly the same as part B. All right, you start to see what is about to happen. All right, so from this point on, you can do the calculation on anything on a PV diagram. Yeah, and you just have to trace each term individually. But it seems to me the easiest one is either the work done or the energy of the system because we have specific way of calculations. Work done, area under the curve. Energy, 3/2 nRT, right? We have formula for those two. It seems like heat, the Q, seems to be the consequence of knowing the other two. Right? Most of the time, it goes like this. Okay, so we attack the easy one first. Either you find out the work done or you find out the delta U, and then you use those information to figure out the heat. That's the way it goes. All right, things can get more complicated over time, but I think you have already learned a lot today. So what I would like to wrap this lecture with is this. We're not going to do like arbitrary curves because it's infinitely many, right? We're going to go crazy if we want to pursue all possible path or whatever. We're going to stick with this 4, guys. All right, and I'm going to showcase you what are these And then once we're done with this, we're gonna stop right here and put this whole stuff in your brain for a weekend. It's an inception technique. And then hopefully by Monday, everything will just fall into places and then you just understand everything and then we move on. Sounds good? All right, guys. The first two is the most common one that we have already kind of like experienced earlier. The first one is a constant volume process. So that's easy, check. Yeah. The line in the PV diagram is simply just a vertical line. The second one is a horizontal line is a constant pressure process. Not big deal, checked. We have seen that. The third one, now we kind of understand it. We kind of, and we kind of recognize this. If the temperature is a constant, the curve that we are seeing here is just the constant temperature curve. So anything that follows this curve must stay at one particular temperature. So if that is the case, it's a constant temperature process. We're going to name this isothermal process. Sounds good? All right. So at least now we have three sort of like a process that kind of like play with our equation of states parameter, P, V, and T. Constant P, constant V, constant T. Make sense? All right. So at least now we have first three. Now the last one, this is the kicker. What if, Ajahn, I have a process that do not allow any heat to exchange at all? That is called adiabatic curve or adiabatic process. All right, so these are the only four that we're going to focus on because knowing these four allow you to pretty much explain, well, most of the engine, most of the air refrigerator, air conditioner, and how those things work under thermodynamics laws already. All right, so these gonna be the four main processes that we try to learn and try to understand and put it into work. All right, so I'm gonna go through this one by one and showcase what is happening and try to focus on the only stuff that is important, all right? Because to derive everything will take too much time. But the first two is easy, guys. Constant volume process, lovely. Right away, Ajahn, this is good. W is 0. W is 0. Delta U must be equal to the heat. Yeah, perfect. Okay, but now there is something that I would like to show you. And this is not very nice, but it's okay. If you kind of like try to get along with this thermodynamic stuff here. If I write the delta U using the formula that we were given earlier, it's going to be 3/2 NR delta T. Yeah. Okay. All right. It turns out I can manipulate this expression just a bit, make it look like this. I put the N first. I wrap 3/2 R together and leave the delta T in the back as before. And because you said this is also the heat, because we already said that in this process, heat and delta U are exactly the same amount. Does this equation look familiar to you? Q equal to delta T. So this one is equivalent to Q equal to MC delta T somehow. Yeah, remember the heat capacity? But of course, we're not going to have mass for the gas. We have number of moles. But the delta T is still fine. That is a change of the change of the temperature. So that's why the numbers in the brackets should represent the specific heat, same meaning. So that's why we're going to call this, we give it some name. It's going to be 3/2 R is C sub V. There you go. We're going to call it the specific heat for a molar gas. Gas, sort of like heat capacity per mole. Think of it that way. Okay. Because we defined this mini C back in the day to be specific heat capacity per kilogram. But because right now the formula is in mole, so this bracket right here should mean is the heat capacity per mole. Okay, all right, not bad. Okay. But don't worry about it. You don't need to know this exactly. I just need the definition. But don't worry, because in reality, you just calculate. Yeah, you don't have to worry about what do you want to call this? What is the name of that one? Don't worry about it. I just need this definition. That's what it is. All right. So that's good. Keep going. Constant pressure process. All right, here you go. This process is annoying because, all right, Ajahn, work done is non-zero. It's going to be area under the curve. That is the work done, but it's still easy to calculate. It's a P delta V. Width times height. That's good. So if you want to know what is happening, you just have to keep going. Ajahn, I know delta U too. It's always 3/2 NR delta T. No big deal. So for you to combine everything to figure out the heat is just delta U plus W. Yes. Okay. And now you know both of them, so you can just plug them in. 3/2 NR delta T plus P delta V. Done. Your job is done. Okay. So once again, you don't have to worry about this that much. Next week, we will extensively go through this whole calculation, right? We're not going to do anything else. We're just going to keep doing this 10 million times until you know how to do it, okay? There's nothing else to do. But I want something out of this today. I can write down P delta V, just like what we had before, PV equal to nRT. So what does it mean? It means, all right, the first term is here. But the second terms, I can write it as NR delta T, right? Use equation of states, PV equal to nRT. And now I can wrap this into 5/2 NR delta T. And I can rewrite it one more round to make it look like specific heat again. All right. So once again, don't worry about this one. I just need the definition. Anything that shows up in this bracket, I can name it specific heat. But this one is coming from a constant pressure process. I have a subscript P for it. That's it. Okay, sounds good? All right. Okay. And as I said, don't worry about this definition that much, but I just need it for the last slide of the day. So this one, we're going to call it C sub P. Here we go. All right, but how to calculate everything on the constant pressure process? You're just doing it one sort of like a terms at a time. You do the work done, you do the delta U, combine the two to get the heat, your job is done. All right, you don't need to understand completely about the definition of the C sub P. That's okay. All right, third one, almost done, guys, halfway already. Constant temperature process, isothermal process. This one is also good because temperature is unchanged, delta U is 0. So when the delta U is 0, what happened? Oh, there must be some typo here, guys. Oh, it's not typo. Okay, right here, it's good. So there is a Q minus W must be 0, or that's it. Heat is simply the work done during this process. But what is the area under the curve in this one then? Then it has to be integrating whatever going on underneath here. Can we do it? Can you do it? If you don't, take the box. All right, this is good. All right, but if you can, this is what's happening, and I'm going to show you, and you're not going to believe it's easy. Yes, serious. It's easy. All right, W is integral P dV. All right, quickly. But always P is coming from PV equal to nRT. So that means P is nRT over V, yeah? All right, so that means I can just put it back and write it as nRT over V. Everyone good? Okay. And the nice thing about this one is temperature is constant. So N is constant, R is constant, T is constant. You are left with just the integral of 1 over V dV. And everyone knows the integral of 1 over V is simply log V. And that's it. That's how you get nRT log V2 over V1. Done. Not bad. All right, it's quite doable. Even though you don't have to do it again, you do it once and you can just take the formula and you're good. All right, so the answer for this one is, if you want to figure out the work done during the isothermal process, you can calculate it from here. Okay, all right, you don't have to integrate ever again. And whatever the amount of work that you get, that is the heat as well. All right, not bad. I think it's already bad. All right, I know. I can see it from your faces. All right. Last one though. Last one of the day. Adiabatic process. The process that do not allow heat to flow. This is the annoying one because, of course, you just play with the condition that heat is 0. So your first law of thermodynamics is down to this equation right here. Q will just disappear. All right, and this is the part that we don't want to derive it anymore. But knowing this, guys, if it is adiabatic, this is the extra condition that you have to follow. Wow. Any adiabatic process, not only PV equal to nRT, not only equation of states has to follow and everything, there is an extra condition that the gas has to follow, which is PV to the gamma stay fixed as well. All right, you probably asking, what is gamma, Ajahn? Yeah, gamma is just a ratio of those two numbers that I defined, C sub P and C sub V. But the reason that I said don't worry about it, because we know exactly this is 5/2 R. We know exactly that this one is 3/2 R. So for monatomic atoms, it's always 5/3. So the gamma is just a number for gaseous system. For monatomic system, the gamma is fixed at this 5/3 ratio all the time. That's why if you ignore C sub P and C sub V, don't worry about it. Grab this gamma, plug it into that condition, PV to the gamma is a constant, you're good to go. Okay, all right, nice. So don't worry about the definition so much, but you just know that if you ended up with this adiabatic process, this is the equation that you have to incorporate into your calculation as well. Whew, that's quite a lot today, yeah? All right, so here you go. So these are the 4 main processes: constant volume, constant pressure, constant temperature, no heat transfer. Next time, we're gonna mix them up, okay? And allow you to calculate everything about this thermodynamics. And once you kind of like get a hang of that one, we're gonna move on to use that to explain the thermal engine. Now you're gonna build an engine that extracts the energy from the heat flow and do something useful. And that's where the car is burning fuel for. You burn the gas and turn the wheel. That is one of the heat engine that we're gonna try to understand. Sounds good? And that's why you're gonna know why the diesel engine is not that good. It's the best that human can do, but it's not that good. All right, and there's so many stuff coming, or why you want to use the hybrid, or at least yeah, you can go electric vehicle. It's better, you know, I don't know, who knows. All right, guys, so that is it for today. Thank you very much. Let me stop right here. That's a lot today, yeah.